That was correct. So you guys
maybe just right up front here. Yeah, just right up front anywhere. Yeah. Good evening. We're going to go ahead and get started. So please come on in and find a seat, and welcome to all of you joining us online. My name is Laura Heisler. I'm Director of Programming for the Wisconsin Alumni Research Foundation, also Director of Outreach for the Morgridge Institute for Research, and do a lot of partnering with the Wisconsin Institute for Discovery. And these are the three organizations that collaborate to bring you the Crossroads of Ideas series. This series takes place once a month during the academic year. This will be our final session for the calendar year 2021. In a moment, I'll share the dates and topics of the upcoming sessions that will begin next semester. Before I do that, I want to mention a few things about how this evening is going to go. So we're going to be starting with some remarks and a video featuring Garth Harmsworth, and I'll be talking about that in just a moment. And then we'll have two presentations, one after the other. After that, we're going to have a moderated discussion with Kayla Wynn from the Cap Times, who will be discussing with Professor Handelsman and Hardemink their views on soil and expanding a little bit on their presentations. And then we will open things up for audience Q&A. If you are here in the room with us, when we get to the Q&A, which will be at about, I should mention, we're going to go all the way up till 8:30 tonight. The Q&A will start around 8:15. If you're here and you want to participate in the Q&A, we're going to ask you that you line up at the microphone here in the middle of the room. If you're participating remotely and you want to participate in the Q&A, please do use the Q&A function of Zoom. Type in your question. I will be your voice and I will represent your questions, and we'll get to as many as we can in that last 15 minutes of our 90-minute evening. So that's how we're going to take things on. I'm going to introduce our speakers now, and then we'll get started with the video from Garth Harmsworth, and then we'll go through our presentations. So I'm going to begin by, oh, first, I forgot, sorry. I want to mention the dates that are coming up for the next Crossroads. Apologize for that. So you might want to mark your calendars if we could have that slide. If we could have the next slide, please. Should I do it? You do it? Okay. We are going to get that slide. So we're, I will mention that this year we've been featuring a series within a series that we're calling Big Questions, where we are bringing a philosopher and a scientist together to tackle some of the biggest questions confronting us as humans. And that series, that mini series within a series, continues next semester. So I do remember these by heart. So on February 8th, we will be talking about what is happiness. So you might want to mark your calendars for that. On March 8th, we'll be talking about what is free will. And then on April 5th, we'll be talking about what is morality. All of those sessions, they're all on Tuesday nights. They'll be right here at 7 p.m. and again, available online as well if you prefer. And then I also want to mention, I just learned tonight, if you're interested in learning more about soils after tonight's sessions, you might want to mark your calendars for February 16th, which is a Wednesday. Wednesday night at the lab is going to feature some methods and findings on soil contamination standards presented by Bob Schneiker, who is president of ESCI. And you'll be able to find all of that on the Wednesday night at the lab website a little bit later as we get a little bit closer. But February 16th is another date if you're interested in learning more about soil. So here are the dates for the spring Crossroads sessions. And now I'm going to introduce our speakers, and then I'm going to introduce a very special representative to talk about the land that we're on. And so we'll be getting to that in a moment. But I want to start by introducing Alfred Hartemink, who is professor of soil science at UW. His main interests are pedology, which I had to look up even though I was a Greek major, which is the understanding and characterizing soil formation, evolution, and the theoretical frameworks for modeling soil bodies, often in the context of the natural environment, straight out of Wikipedia. And he's also interested in the fostering and epistemology of soil science. Our next speaker will be Joe Handelsman, who is the director of the Wisconsin Institute for Discovery in this building, and a Vilas Research Professor and Howard Hughes Medical Institute Professor in the Department of Plant Pathology here at UW-Madison. She previously served as a science advisor to President Barack Obama. Her research focuses on the role of small molecules on the structure and function of microbial communities. In the course of this work, she has discovered several new antibiotics from soil bacteria by traditional culture-based methods and metagenomics. She is the founder of Tiny Earth, which is a consortium of college instructors and students across the world dedicated to discovering new antibiotics from soil bacteria. And she has just released her new book, which you can buy tonight and get signed, called A World Without Soil. Before we hear from Professors Hartemink and Handelsman, though, we will be learning about the knowledge and perspective of Maori values guiding the wetland restoration efforts in New Zealand. This project resulted in handbooks that have been made available for free. Garth Harmsworth is a senior environmental scientist based in Palmerston North in New Zealand. And over the last 30 years, he has pioneered much of the Maori-led research by working on a wide range of projects with Maori organizations, including government agencies, regional councils, industry, and communities throughout New Zealand, particularly in areas of land use planning, ecosystem health, restoring indigenous landscapes, collaborative learning, and indigenous Maori language, knowledge, values, and much more. Yvonne Tora is an early career Maori researcher in Manaki, Wainua, and I'm not sure if I got that pronunciation right, I apologize. And Bev Clarkson is a senior wetlands ecologist and world expert on wetlands. Together with Garth Harmsworth, they recently published the second volume of a series of handbooks about New Zealand wetlands titled The Voice of the Wetland, I Am Still Here. Garth insisted that these two editors and staff receive credit for the handbook and present to you tonight. We hope you enjoy the discussion of these important resources. As we hear about the Indigenous Maori perspectives on land use, let us also acknowledge the Indigenous knowledge found in the land we stand on here at UW-Madison. And I'd like to invite WID's Communications Director, Laura Red Eagle, to give us a brief land acknowledgement in Ho-Chunk. Laura, please come on up. And I'll just say, following these presentations, that's when we'll have the discussion with Kayla Wynn. So if you could, and then Laura, we'll have you just cue the video after your comments, if you can.
Ha, hija kishana hini karagiwi. My khade rajra Laura ready go ga hingaire. Egi Ho-Chunk rajra chachshets ga hingaire. Egi hamte e woish aki u anaga dejo pregi. UW-Madison nagre. Ho-Chunk wazi eja chira naga hija kirashana. Wangshi hija hi. Egi chinankara wawi karagire. Ma wakanchunk hanaji harajawira Ho-Chunk wazi achi wangshikra egi hanihaire. Today, with great respect, here in Madison in the UW, as along the Ho-Chunk, along with the other tribes, recognize that this town is in sacred land. This village, this town is on sacred land, and we are all still here. Hegu kira.
Tātou katoa. It's a privilege to be presenting to you today. Ko waio he ritianei no nai tirangi Ngāti Ranginui, Ngāti Tūwharetua, Ngāti Uanaku Ngā Iwi. Kei te mahi au he karangahau Māori mō Manaaki Whenua. So tēnā tātou everyone, I'm Yvonne Toda. I'm a kairangahau researcher at Manaaki Whenua Landcare Research, which is a Crown Research Institute here in Aotearoa, New Zealand. I'm also the Vision Mā Tauranga lead for the Wetlands program led by Manaaki Whenua. So I've been privileged to work alongside Shariva and Shepard Goodman and Beverly Clarkson to create this stunning cultural wetland handbook series, Te Reo Te Repo, the voice of the wetland. So Bev and I will be sharing with you our wetland handbook series and specifically focusing on our recently launched handbook, Te Reo Te Repo, Kei Konei Tonu Au, the voice of the wetland, I am still here. So I'd like to acknowledge Cherie, our other co-editor, who unfortunately couldn't join us today. So I'll now pass the baton on to Bev to introduce herself.
Kia ora koutou, ko Bev Clarkson toka ingoa, no Turanganui a Kiwa ahau, kei kirikiri rā I noho ana I naenei, kei Manaaki Whenua I mahi ane, kia ora. Greetings everyone, my name is Bev Clarkson. I'm a wetland plant ecologist at Manaaki Whenua Landcare Research based in Hamilton in the North Island of New Zealand. Kia ora. Wetlands are important because they maintain water quality, sequester carbon, and sustain unique plants and animals. Wetlands are valued by Māori for their spiritual and cultural significance and as important sources of food and resources closely linked to their identity. Despite this, New Zealand has lost more than 90% of its original wetlands, and remaining wetlands are steadily degrading. Our wetland program at Manaaki Whenua Landcare Research has developed a series of handbooks covering technical and cultural aspects of restoring wetlands. The 3 handbooks shown here are all available free to download on the Manaaki Whenua Landcare Research website. Our first handbook in the wetland series was published in 2010 and arose from a need for best practice restoration techniques to assist landowners, community groups, and the wider public in improving the condition of our wetlands. The work focused on biophysical aspects such as restoring the hydrology, nutrients, and the native plants and animals. The handbook highlighted an important gap on cultural perspectives for enhancing repo to address iwi priorities and aspirations for the health and well-being of their wetlands. So the next handbooks in the series focused on this gap.
So at this time, there was no real platform to acknowledge the amazing wetland restoration work that Māori were doing to reconnect to their wetlands and rediscover the important wetland cultural values for Māori. So in 2017, we collaborated with Waikato Tainui, who is an iwi authority in the Waikato region of the North Island, and published Te Reo Te Repo, the voice of the wetland. So the ability to share stories of our people were important to our research partner. So we embarked on creating a resource that focused on a Te Ao Māori perspective, or a Māori worldview of wetland restoration. The handbook includes processes for facilitating renewed and vibrant connections between whānau or families and their resources, understanding our cultural resources, and learning from case studies on wetland restoration, cultural indicators, and monitoring, all led by or in collaboration with Māori. So with the success of Te Reo Te Repo, we embarked on a second edition of the Cultural Wetland Handbook series. Te Reo Te Repo Kei Konei Tono Au continues to advocate the voices of the wetland through the voices of our people. The voice of the wetland, I Am Still Here, showcases the remarkable stories and wetland projects that some of our Māori communities have done since 2017. But this time we were hit with a global pandemic, a very new political, social, and environmental landscape for Māori to deal with and adapt to. Also, the awareness that we were on the brink of losing our mātauranga or Indigenous knowledge for some of our unique taonga or treasured flora and fauna species, which deserve to be highlighted in this handbook. So this handbook acknowledges the change in focus for some of our whānau. So we are very delighted to be providing you with a snapshot of Te Reo Te Repo Kei Konei Tono Au. So where did we get the name for our handbook? And this is spoken elegantly within this whakatauki. Ka mea ake te repo me he manawa whenua, e kore taku reo e ngaro, kei konei tonu au, kei konei tonu tātou. The wetland replied, my voice will never be lost. Like a spring a burst forth from the land. I am still here. We are all still here. So at this time of global uncertainty, it was our wetland who were loudly signaling to us that they are still here and that we as a people needed to listen. So we are still guided by the voice of the wetland. So there are 3 sections within our handbook, and the first one is process of engagement. So all of the illustrations you can see here were commissioned by a local artist who also is a wetland conservationist herself, to really help bring to life the wetland ecosystems of Aotearoa, New Zealand. So yeah, they're quite beautiful, aren't they? So one of the chapters from this section is the work from an iwi charitable trust in the Waikato region of the North Island. This chapter talks to the innovations of adapting to a rapidly changing working environment under the new COVID restrictions. And thanks to the guidance of their tupuna or ancestors, this iwi-led environmental-based charity was able to push beyond challenges and continue to strive for their community. The chapter also outlines the process of their recently developed Māori wetland framework that was developed aligning to iwi and hapu values and priorities for wetland restoration. So this is the conceptual illustration that focuses on the main themes and values identified by whānau in order to prioritize wetland restoration efforts.
The second section is cultural resources and focuses on flora and fauna species considered important to Māori. The chapters also showcase threatened wetland species to help rebuild mātauranga or knowledge and better support the health and well-being of wetlands. They include Sparadanthus ferrugineus, an important pet former, tuna or eels, highly valued for food, wetland paddlers such as the grey duck, and molecular research on Māori medicinal plants which have potential to treat type 2 diabetes. For example, this chapter interweaves culture, science, and arts with the endemic threatened species Sparadanthus ferrugineus. Sparadanthus once dominated large peat bogs in the northern North Island, but because of widespread drainage and conversion to agriculture, it is now confined to a very few isolated populations. The loss of the plant has also resulted in loss of traditional names and customary practices associated with Sparadanthus. The Maori proverb on the slide is very fitting, as Sparadanthus is in the family Restianaceae and snaps very easily at the joints all along the stems. When reeds stand alone, they are vulnerable, but together they are unbreakable. So although individual stems are easily broken, clumps of the stems are impenetrable or invincible. This reflects the plight of Sparadanthus because we need to increase the number and the size of the populations before it is too late. The Sparadanthus stem is home to a very skinny caterpillar nicknamed Fred the Thread, the not very hungry caterpillar. Fred was discovered by our invertebrate ecologist, Corinne Watts, and she and colleague Robert Hoare reared Fred through to adulthood to emerge as a moth, which was new to science. So they named it Houdinia flexillissima, after the great Harry Houdini, the famous escape artist, because of the way Fred escapes from the tight confines of the Sparadanthus stem. Fred inspired Robert to write this poem. I have a friend, his name is Fred. He's thinner than a cotton thread. His colour is an orange red. He doesn't feed on jam or bread, but Sparadanthus stems instead. The remaining verses are in the chapter.
Yeah, please go check it out. It's such a gorgeous poem, and it's made use and it's been transmitted throughout a lot of our classrooms throughout Aotearoa. So our third and last section of the handbook is Mātauranga Māori and explores the knowledge and whakapapa or cultural connections for wetland restoration by Māori. So here are a few images of our Māori communities or iwi and hapu interacting with their wetlands, prioritizing wetland restoration efforts and utilizing cultural resources. So one of the chapters in this section outlines the process we took to transform Te Reo o Te Repo, the Cultural Wetland Handbook series, into online educational resources for school classrooms. So we were privileged to work alongside science educators, Māori educators, and advisors to develop bilingual wetland educational resources suited for Māori immersion language schools, which is kura kaupapa, and mainstream audiences to reconnect them to their local wetlands. So while developing the resources, we were reminded once again, how do we heal a wetland? Well, you ask it. So it's really that simple. The Te Reo o Te Repo Cultural Wetland Handbook series is recognisably Māori or Indigenous to Aotearoa, New Zealand. So we talk about whakapapa, connections and genealogy, and how as us as a people, we are connected to our environment. So here we have illustrations of the female deities connected to water and their relationship to wetlands and their important role in their creation. So it was important for us to acknowledge our creators and atua, or gods and goddesses, that are responsible for our specific environmental domains, even more to highlight the feminine deities of these domains. So here we have Hini Te Repo. She is the green goddess here. And the artist who responsible for these designs is a Māori female Māori artist who specializes in tamoko or traditional tattoo. So she was very specific in creating Hini Te Repo by utilizing concepts and elements of our wetlands throughout Aotearoa, and recognizably feminine by the moko kauai or the tattoo on her chin. So we were very, very fortunate and a great way to acknowledge our feminine deities within this handbook.
We would like to thank many, many individuals and organisations for contributing to and supporting this work. They include Waikato Tānui, environmental organisations, research institutes and universities, and our main funding agency, the New Zealand Ministry of Business, Innovation and Employment.
Te Reo o Te Repo Kei Konei Tonu Au is now available for free. free download on our Manaaki Whenua website. And if you'd like to check out all of the 3 handbooks that we've published, they're all accessible on the webpage Wetland Handbook Series. We hope you are enticed to take a look at our Wetland Handbook Series and learn more about the work we have done in Aotearoa to connect, understand, and learn more about the wetland cultural values. So thank you for joining us today. We hope you check out our handbooks, and ngā mihi nui kia koutou katoa. Ka kite.
Yes, thank you. So some years ago, I had dinner with Marv Beatty. And Marv Beatty is a professor of soil science who obtained his PhD in 1955. And Marv is obviously a bit older than I am. And that night, Marv told me a story about 2 people that sort of fascinated me. He talks about a young graduate from Michigan Agricultural College named Charles Kellogg, who traveled in 1929 from East Lansing, Michigan to Fargo, but stopped on his way in Madison to visit with Emil Truock, professor of soil science. And Truock asked him what he's going to do. He said, I'm going to Fargo for a job interview. And Truock looked at him, and he had sort of an old shabby suit on. And I guess, 1929, obviously the crisis being very near. So Truock gave him money to buy a new suit and a new shirt and a new pair of shoes. And that's what Charles Kellogg did. And he bought that, got in his car, drove to Fargo, was interviewed for the position and got the job. And that in itself is kind of a nice story. But the thing with Charles Kellogg, he stayed about 3 or 4 years in Fargo and then moved on to DC, where he became the chief of the soil survey for about 40 years almost. And no one has had a better influence on the way that the soils have been mapped in this country than him, Charles Kellogg, so to speak. And in 1950s, when it came to the decision where to hold the 7th International Congress of Soil Science, which was a big thing, there were a couple of competitors. One of them was Purdue, the other one was Cornell. But Emil Truock was very keen to have the Congress in Madison. And Charles Kellogg, who was essentially then already very influential in the government, got a phone call from Truock and remembered about the suit and the shoes that he was given in 1929. And hence, in 1960, the 7th International Congress of Soil Science was held in Madison as a result. He would say a small little story, and I decided to write up that story and a few others. And that's what became of it. And so my love, Elise Fatura, asked me who would read these stories. And I thought about 10 people. So I'm very glad that all of you are here. Yeah? All of you are online too. So that is good for the circulation. Now let me meander. I will read a few things if you allow me. Let me meander a little through the beginning of soil science in the US, and then I will read some sections later on as well, with your permission. As long as people have cultivated the earth, they have observed the growth and fruits of what they planted. As nature showed them, they distinguished which plants grew well on different soils. Observation didn't bring much understanding, but was needed for mimicking nature so as to avoid failure. While experience became tradition, the world underfoot was largely unknown to the early cultivators. Some tried to manipulate nature and mend the soil so that plants grew better and yielded more. They dug ditches so excess water was drained. They applied ashes or limestone to feed their crops. And all of that generated a lot of practical knowledge that was passed on from generation to generation. And the world could have been left in those spheres for millennia easily, but it was not. It was not. People figured out the scientific method to advance knowledge. And that of itself is possibly humanity's most successful discovery. The New World, the Americas, was an unknown land for the European travelers, colonizers, and freedom seekers who set foot in the early 1600s. But it wasn't a new world, nor was it uninhabited. The Clovis people had arrived some 24,000 years earlier from Beringia, and millions of American Indians lived all across the land. European colonists claimed the discovery of a land that had been settled for thousands of years. Soil observations in the US began with the American Indians, who had transformed from nomadic to sedentary lifestyles, started growing crops, and discovered the diversity and peculiarity of soil. But that empirical knowledge, gained over many centuries, millennia, was ignored by the European colonizers and travelers. And I will give some example of those early travelers that came here. In the late 1700s, a French traveler named Constantin Volney voyaged for 3 years through the central and eastern part of the colony with the purpose of studying the climate, laws, people, and their manners, chiefly in relation of social and domestic life. He observed, to a traveler from Europe, the most striking feature of America is the rugged and dreary prospect of an almost universal forest. The ground beneath it was sterile and rough, or encumbered with the fallen and decaying trunks of ancient trees. Among the inland mountains, trees are found in such numbers, and their prevalence is so little checked and circumscribed that the United States may justly be denominated one vast forest. He also had an interest in the climate, an opinion, as he wrote, an opinion of late years gained ground in the United States that partial changes have taken place in the climate of the country, which have shown themselves in the proportion as the land has been cleared. Summers were perceived to be hotter and winters colder, and he concluded, there seems no room to doubt the truth of a sensible change in the climate of the country. That was written in the late 1700s, yeah? Still, some people find it hard to accept, I believe. For Europeans, America was a magnet, and some of that attraction came from a book from 1869 entitled Where to Immigrate and Why. It listed the climate, soils, price of farmland, and a range of conditions, including railway and law and land descriptions. Wisconsin was described as having a cold but agreeable climate, and the soils were remarkably productive and would create extraordinary wealth in production and quality of wheat and maize. Settlers' experience did not match those roaring descriptions, particularly in the East. Crop yields declined after some seasons, and the settlers developed the notion of soil exhaustion, which was used to describe a variety of conditions, including soils that were affected by erosion and depleted of their fertility. Exhausted soils were also termed tired or sick or out of condition or worn out soils. And it was assumed that all these soils were equally productive and broad under cultivation, but many soils were already of low fertility before they started. Soil exhaustion was caused by continuously cropping, lack of knowledge how the soil should be made or kept productive, and some carelessness. As the historian Avery Craven, whose parents had left North Carolina because of slavery and racism, explained in the 1920s, frontier communities are by their very nature notorious exhausters of soils. The wants and standards of living of such communities have been developed in older economic regions, and they make demands upon the newer sections that cannot be met from normal returns. The abundance of land, combined with a scarcity of capital and labor, a condition which characterizes all frontiers, throws the burden of intensified production upon the soil as the cheapest factor. The problem is one of rapid spending, not of conservation. Frontiers, like those who come to sudden wealth, are inclined to spendthrifts. One person who was particularly interested in soil exhaustion and who was born in a frontier community was Emil Truock. He was born and raised in Independence in Trempealeau County, and I will read a bit about that region. The glacial ice that concealed all the land in the north left a chunk of Wisconsin untouched. It was polar cold, but the ice didn't rub over the landscape, crush and flatten its rock, nor did it deposit till or drift, but unsorted angular and rounded rock rubble. The unglaciated land became known as the driftless area and covers about 1/4 of Wisconsin. Its bare land mass stood as uncrushed sedimentary rocks, which were formed tens of millions of years earlier when Wisconsin was situated in a tropical lowland. Strong winds blasted the barren land after the glacial period, and storms picked up fine silty deposits from the Missouri and Mississippi rivers and carried them eastwards, blanketing the old sedimentary rocks. And on those winds, a new landscape was born. The rugged terrain had some steep bluffs and broad valleys that were covered by silt, and this silt cover was thicker closer to the Mississippi. Soil slowly grew in these silty lush, and from the weathering of the underlying rock, that was rich in calcium and magnesium and fossilized organisms. When the earth warmed up, plants carefully colonized the new ground, but bitter coldness returned annually, laying waste to all greenlands, and for many months the land would return to its glacial state. Then came spring, and the warmth and rain revived green lushness, and the soils graciously harbored roots and decaying plants. Colorless carbon that had been chemically fixed by the plants from the air was brought into the soil, where it was decayed into black organic matter. Minerals absorbed water, broke apart and released nutrients that were taken up by the plants, and what was not taken up was held onto by the finest soil particles. The soils were alive. An invisible web of bacteria and fungi orchestrated the rearranging of every particle in the soil, whether it was alive, dead, or had never lived. Soils formed differently on the hills than in the valleys, and on the grass or on the trees, but they were all young, and their distinctness grew with the passing of each season. In 1850, the Truog family immigrated from Chur, a 13th century village in eastern Switzerland, to the US. The family sailed across the Atlantic, landed at New Orleans, and took the steamboat up the Mississippi River. They settled in a Swiss colony in the western part of the state, and in the hills they could raise and milk cattle and make Wisconsin cheese. In 1884, they bought a farm in Independence, some 40 kilometers from the river. And within a year after they had settled, Thomas and Magdalena Truog had their 10th baby. They named him Emil. When Emil grew up, he worked 6 months each year on the farm and went to school for the other 6 months. And at the age of 14, it became clear to him that there was no future on the farm. And his teacher suggested that he continues his studies. At home and in the library, he started reading farm magazines that focused on how cropping exhausts soils. There were articles on the restoration of nitrogen by legumes, and that phosphorus and lime would have to be applied, even though those nutrients were returned in the animal manure. The Truog land had been cultivated for 25 years and showed signs of soil depletion. They looked for land in Iowa, but thought that much of the state was a swamp, which was indeed the case before the trial drainage were installed. Thomas Truog thought that Emil should attend a short course in agriculture at the University of Wisconsin. That was taught during the winter months. But Emil preferred to enroll in the 4th-year course that would lead to a university degree. And in 1905, he enrolled in the agricultural program here. Thomas Truog had often told his son that production of good crops never failed on new lands. But with cropping, the luxuriant growth of new virgin land declined rapidly. It was clear for Emil Truog that he should find answer to these problems. He received a BS degree in agriculture in 1909 and obtained a master's in chemistry in 1912 under the supervision of Victor Lenheer, who was an expert in research on chemical warfare and studied the chemistry of gold, tellurium, and selenium. Lenheer was ready to accept the PhD thesis from Truog, but came afflicted with a strange sickness, possibly as a result of some poisonous chemical that he had studied. As Lenheer was seriously ill, Emil Truog became involved in teaching and research and didn't find time to go through the formalities of submitting the thesis. He never obtained a PhD degree. In 1912, he was hired as an instructor in the Department of Soils. And at that time, the geologist Charles van Hise was the president of the university. The university grew rapidly, and the number of professors quadrupled in 15 years. Charles van Hise founded also the Extension Division, as he felt that the work at the university should benefit the entire state. As part of that growth and investment, Emil Truog was hired. Truog's main goal was to develop a soil test that all farmers could use, in particular soil pH test. There was an indication for how much lime should be applied. He called an acid soil chronically sick, and lime was the cure. Truog was convinced that soil testing was essential for managing the fertility of the soil, and together with Andrew Whitson, he convinced in 1913 Wisconsin state lawmakers to provide funding for the establishment of the state soils laboratory. That laboratory was written into law. One of the first tests by the state laboratory was a litmus paper for soil acidity that he had developed. And he had observed that liming was highly beneficial for legume crops like alfalfa, as nitrogen-fixing bacteria, the rhizobia, are affected by acidity, and lime improves the nodulation. It delighted him to work on an issue that was his first name spelled backwards. Having been born on a farm, Truog was well aware of the fruits of frugal, patience, and hardworking life. For him, there was no substitute for perseverance and for the seeing eye and inquiring mind. He spent 42 years at the Department of Soils and was a mentor to 103 PhD and 72 master students. He mentored Marion Jackson, who mentored Champ Tanner, the first Wisconsin soil scientists to become members of the National Academy. Emil Truog trained no female graduate students. The first female that graduated with a PhD from the Department of Soil Science was Jaya Iyer in 1968, followed by Mary Beth Kirkham in 1971. Truog officially retired in 1954, and some years later, he was nominated for an honorary degree at UW, where he had worked since 1912, and where he had largely built the Department of Soils. It was not awarded. All right, those are just some stories, folks. And I could go on, but I want to make one last comment, sort of. When studying the development of soil science in the US and across the globe, I should say that there's a big web of connections between people and institutions and universities and centers and countries. And the more you look into it, the more amazing it is. And I often thought by myself, it's a small world. It is really a small world. And one wonders why we can't take care of it. So with that, I'll like to introduce the director of the Wisconsin Institute of Discovery and a very eminent scientist at UW-Madison, Dr. Joe Handelsman. Thank you.
Well, thank you, Alfred, and thank you, everybody who made this day possible. We decided to celebrate.
I'm just going to get your presentation.
Okay. We decided to celebrate World Soil Day, which was this past Sunday, by celebrating 3 books that just came out within the last few weeks, practically at the same time. So I hope you enjoyed hearing about the Maori soil science book, which is an amazing fusion of Maori philosophy as well as science. You've heard from Alfred now, great history of, thank you, of soil science in Wisconsin, which really has a very illustrious history. And I'm going to tell you now about the book that I wrote called A World Without Soil, which started when I was in the White House. I worked for President Obama for a little over 3 years at the end of his administration, acting as a science advisor. And I had many, many issues, from precision medicine to dealing with telescopes. But one that was very close to my heart, because I've always been a soil microbiologist, was saving soil and training more soil scientists. But what I had missed was that the soil loss crisis had reached a new pitch. And I was shocked that here I was, a soil scientist for decades, And I didn't realize that the world was in the danger it was. So I started getting tutored by a soil scientist at Iowa State and several others around the country, and began to become really convinced that we have a problem and it's not being talked about. And so I decided when I left the administration, because I had not made the kind of progress on soil policy that I had in other areas, that I would write a book to try to influence the future of soil. And so the book focuses on the substance that is so familiar. We walk on it every day. We call it dirt, unfortunately. And it's in very many different shapes and forms around us and under us. But what is soil really? We take it for granted, but in fact, it is one of the most fascinating ecosystems in the world, and clearly the most complicated. So it's a mixture of many things, which is why the complexity is so enormous. It's geologic, it has minerals that come from the rocks in the earth. The sand, silt, and clay particles are the different size particles, different chemically structured particles that make up the geologic part. Much of the rest of it is either alive organisms, bacteria, fungi, nematodes, plants, and other animals, or ones that are decomposing. And a lot of what's in soil is actually decomposing life that was. One of the things that is really striking to any soil scientist is that the biggest ingredient in soil is time. It takes a long time for soil to form. So on the left here, you see a very young soil. It's a soil that has not differentiated yet into what we call the horizons, which are shown in the soil on the right. These layers that you can see of different colors, those are different geologic states. That's the effects of weathering, which is the process of changing the chemicals and minerals in the soil. And you can see there are different states of differentiation. But what's most striking is that and I think the reason many people think soil is a static thing is that it forms pretty slowly. So it forms at about 0.5 ton per acre per year, which doesn't really mean too much, but I hope it will in a few minutes when we talk about the rates at which it's lost. So 0.5 ton per acre is about 1/100th of an inch. So that's not very perceptible by our standards. And so soil that we're looking at today, the mature soils and the soils of Wisconsin, are hundreds or thousands of years old. They have been forming for a very long time. And yet we are eroding them, destroying them at an incredible rate. That is particularly alarming because of the number of different reasons that we need our soil. So the obvious one is food security. 95% of our food supply comes directly from things that grow in the soil or the animals that are fed those things. So we can't produce enough food, no matter what happens with some of the modern techniques of aeroponics, hydroponics, greenhouses, vertical farming. You've probably heard some of these things talked about. There is no way that we can feed the human species with any of those methods. We need soil. Water quality is totally predicted and determined by soil. In fact, soil is the biggest water filter that's laid across the entire earth. It has the capacity to take out impurities, to destroy toxins, and to purify the water. I mean, if you think of the water as a puddle in your driveway, you probably wouldn't want to drink that. But when that very same water percolates down into the groundwater, you pump it up and you do drink it, and it's quite clean and pristine. That's because of the bacteria and the minerals, the organisms in soil that purify that water. Soil is the home to an enormous amount of biodiversity on Earth. And so when we destroy soil, we also destroy organisms that may not exist anyplace else. Antibiotics come from soil. Between 2/3 and 3/4 of all the antibiotics we use in medicine today come from soil bacteria. So, and there are many other drugs, but the antibiotics, the most prominent and evident ones that come from soil. So again, if we lose soil, we actually don't know what we're losing, but we may be losing biodiversity that gives us the incredible variety of drugs that we have available today. And a very minimally recognized property of soil is carbon storage. So soil contains 2,500 billion tons of organic carbon in the top 2 meters on Earth. So 2.5 trillion tons of organic matter. That's organic carbon. That is a lot of carbon. In fact, it's 3 times as much as all of the carbon in the atmosphere around the Earth. So the entire atmosphere has 1/3 as much carbon as the soil carries in it. And it's about 4 or 5 times as much as we find in all the plant biomass. So when you hear all the stories in the climate discussions of how we have to worry about the forests and the plants, that is true. But what those arguments often will ignore is we need to pay attention to the carbon in soil. That's a tremendous source of carbon or repository for carbon. So where does that carbon come from? It's worth just reviewing very briefly what leaves carbon in soil. So plants grow using the energy of the sun for photosynthesis. Photosynthesis fixes carbon from carbon dioxide in the air to molecules that become part of the plant. And eventually plants secrete a lot of their carbon from their roots. So it leaves the plant and it enriches the soil. So much of our soil carbon is the carbon that is excreted by plants into the surrounding soil. I find that a particularly interesting fact that plants will secrete about 1/3 of their carbon that they fix into the soil. You know, obviously evolution doesn't produce that kind of apparent waste. So there has to be a purpose for that, a benefit to the plant for it to so-called waste all that carbon on the soil. Well, of course, what it's doing is feeding its friends in the soil and feeding the soil itself. The bacteria in the soil produce a kind of glue that sticks soil particles together. And when soil particles are stuck together, they're much less likely to move or erode because they're in clumps or clods that have much greater density and mass. So the sad thing is that today we know that we've lost about 50% of the carbon that was in soil around 1850. And that's largely due to agriculture. So half of the carbon that was there is no longer there. If it's eroding that quickly, so half of the carbon eroding in about 170 years after it took many centuries to form, what are we going to do without our soil? And why is it eroding so quickly? So it's worth looking at some of the causes of soil erosion and also what we can do about it. So the 2 forces that move soil from a field, from a soil site to some other site are wind and water. And wind, I think, causes really spectacular events. This is an example of a windstorm in India. And there are many examples like this in the United States. Probably many people have seen the pictures of the Dust Bowl where soil was being taken off the land by the wind at incredible rates. And so you see a very dramatic event above ground. And across the world, the wind redistributes about between 1 and 4 gigatons of soil each year. And that's a very important process because it means that some parts of the world lose their soil and lose the minerals and nutrients with it, and other parts of the world benefit. So for example, the Sahara Desert donates many tons of soil to Brazil, for example, whose soil is enormously enriched by the minerals that come from the Sahara Desert. The water that erodes soil is not always as evident because a lot of what happens is on the ground and in the ground. So it's not causing these plumes of soil in the air. But it's the most significant force that erodes soil. And just to give you a sense of what it's like to be a soil particle in the path of a raindrop, If you had 40 inches of rain, which is not that much more than we have, for example, in a year in Wisconsin, on 2.4 acres or a hectare of soil, you would be experiencing the force of a ton of TNT explosives. So that's the force that our precious soil particles are dealing with when the rain is pummeling them and destroying their clods. The third major force that damages soil is human intervention. And I would say that the most influential part of that has been the plow. This is an example of a plow that Thomas Jefferson invented. And he thought the plow, he said that it was the greatest invention of all times. And being the enigmatic and contradictory person that he was, he absolutely loved farming and he loved nature and he respected the soil enormously. And yet he created a plow that used an iron foot to go into the soil and flip it over. And the process of plowing, of course, opened up land, made it possible to plant seeds in furrows, but it also made the soil extremely vulnerable to erosion and probably caused enormous amounts of erosion right under Jefferson's nose. He didn't talk about erosion in his letters and his papers until later in his life. He wrote one letter that I found that talked about this brilliant son-in-law of his who had started to plow around hills rather than up and down them. And it's, of course, much easier for soil to move downhill with up and down furrows. And he recognized that that was going to preserve soil. But he somehow never made the connection that this invention of his that he was so proud of, took 5 years to design this plow, was in fact the cause of soil loss. And I don't know if he did, we'll never know, I guess, if he did recognize that before the end of his life. But there's been a lot building on this famous plow. It's called a moldboard plow of Jefferson's. Soon after he invented the moldboard plow, people began to move west from the East Coast. As Alfred alluded to, the soils got tired. The soils ran out of nutrients and support for plants. So massive populations of European settlers moved toward the Midwest. And as they got there, they found that the plow that Jefferson was so proud of didn't work as well because the soils in the Midwest are much stickier. And so they will adhere to the iron in that foot that makes the moldboard plow. And so a man named John Deere in 1837 said, I think I can improve that. And instead of using iron, I can use steel. And that solved the problem. It turns out that soil doesn't stick to steel the way that it does to iron. He built first 1 and then 10 and then 100 of these plows, and they were so popular that he started a company, which we know today as the John Deere Company. Today, the John Deere plows look quite different, and some of them work just the way the old ones did in that moldboard fashion, but most of them are a little bit kinder to the soil today. And I think it's very heartening that John Deere is today one of the leaders in soil sustainability and soil health. So they recognize that the damage that plows did, their implements did to soil over almost 2 centuries, needs to be fixed, needs to be addressed. And they are quite serious about building not only new tractors, new equipment that goes on soil, but finding biological solutions for the soil loss problem. So when wind and water and plows come together, the results are pretty frightening. If you look across the United States, the average loss of soil from any acre of land, agricultural land, is about 5 tons per year. And that doesn't sound too threatening, but the story gets worse. The 5 tons completely ignores an entire type of erosion called gully erosion. There are 3 types of erosion. And the one that forms these deep gullies, and I'll show you some pictures, is not even included in the national estimates of soil erosion. And many soil scientists have said that they think gully erosion may be as much as half of the soil loss. So already we may be doubling our real numbers. The story gets worse when you look at climate change. Severe weather events where the rain is coming down very hard at high velocity is very damaging to soil. And we are vastly increasing the frequency of those events due to climate change. In the first half of the 20th century, there was a pretty average, consistent amount of or number of high velocity rain events each year. And since 1950, that number has risen very steadily and keeps going up faster and faster. And it has never returned to that average of pre-1950. So we're only going to be seeing more of these very aggressive, severe rainstorms that are so damaging, particularly to Midwestern soil. And an example of what these can do is remember that the average of the entire, across the entire country of soil loss is about 5 tons per acre, and that's probably an underestimate. In Iowa, just a few years ago, there was one rainstorm in which thousands of acres lost as much as 50 tons per acre. There's one afternoon, they lost 10 times the national average of soil loss. And those kinds of rainstorms are no longer rare events. They don't happen once a decade or once a century. They happen many times a season. And so if we don't take care of this problem, we're going to be looking at a very depleted world in terms of soil. So when I was in the White House, some of my staff and I tried to estimate how long will the soil last. That's what everyone wanted to know. And if you look at the top line here, that's if we were losing a kind of common Iowa type soil where it's about 1,000 tons per acre of topsoil. If we were losing it at the average, the national average of 5 tons per acre per year, you can see that by about a century from now, we would have about half the amount of topsoil that we have today. It's at that point that crop yields start to really plummet. When the soil gets to be about half of the depth that it was, that's when farmers begin to see a really devastating loss. But you might say, 100 years from now, I'm not going to be around, so maybe I shouldn't worry too much about that loss. But it's probably not going to keep at that rate of 5 tons per acre. And certainly in some areas of the country, it definitely will not be 5 tons per acre. So if you look here, we have 25 tons per acre. Using that number, a typical Iowa soil would be gone in about 40 years. At 50 tons per acre, we would be down to the subsoil by 2040. And at 100 tons per acre, which has now been observed in some of these terrible storms that we have in the Midwest, at 100 tons per acre, that land would be out of topsoil in less than a decade from now. But the story gets even worse because we're already there with a lot of our farmland. 25% of Iowa's farmland has already lost all of its topsoil. All of its topsoil. That's 25% of one of the richest soils, one of the most fertile states in the country. I find that particularly egregious because in the Midwest, and Alfred disagrees with me on this, but my favorite soil is the mollisol. And in the Midwest, we have this beautiful soil that we think of as that black, rich, dark, fertile material that's been forming for a very long time. And one of the reasons that it formed to become so fertile is that before European Americans came to this part of the country, there were plants that looked like this. Some of the plants, they were perennials, so they come back every year. And they had massive root systems, and those that still exist still do have those root systems. There are examples of switchgrass and other perennial grasses that have 14-foot root systems. So from the surface to the tip of the roots, 14 feet. In contrast, you look at a little corn plant, and that's pretty, in my opinion, very pathetic little root system. So imagine, first of all, the amount of carbon that's being secreted by a root system of this really vast proportion compared with the amount that's being secreted from this little tiny corn plant with its puny roots. And it gets even worse than that, because a perennial plant, the plants that form the Great Prairies of the United States, will deposit most of its carbon into its roots at the end of the season, because it has evolved to preserve its energy and carbon for the following season in the roots. So during the winter, it's not in the upper part of the plant, it gets stored in the roots. So at the end of a season, a perennial will typically leave about 70% of its total carbon in the soil. In contrast, an annual plant, one that you harvest and then it dies every year, like corn, puts most of its energy at the end of the season into producing what we think of as the harvest, the seed. And the result is that by the end of the season, corn plants typically have left 1% of their carbon in the soil. So 1% of the carbon versus 70%. Thank you. So that's a little bit of why the soil is being so depleted, that for centuries we had large animals like bison roaming the field, roaming the prairies. We had these magnificent plants with deep roots, perennials, depositing massive amounts of carbon and then being further fertilized by the animals that roam there. And that's how these soils formed over a long time. But a third of the Corn Belt, which is the region that we're in, has already lost all of its topsoil. So we have squandered this absolutely incredible resource of one of the most productive soils in the world that is actually not that common. It's found in the United States, in part of China, a little bit of Argentina, and where it is really at its pinnacle, the mollisol is in Ukraine. And this is something that I really loved reading about when I was working on the book. I definitely want to go to Ukraine someday to see their soils. They actually have a special name, Chernozem, which in Russian means black earth. And it is well named. The mollisol of Ukraine can be as deep as 5 feet of topsoil. That's more than twice any soil I've ever seen. So I want to go see that someday. And this has not been lost on leaders across the world, that the mollisols, and particularly Ukraine's mollisol, have a really tremendous fertility that could feed a lot of people. It's pretty well demonstrated that Hitler invaded Ukraine for its soil. He didn't think the German people could feed themselves on the land from Germany. And so he tried to take Ukraine as a source of food. More recently, there have been several invasions by Russia, which really wants the Ukraine back because of its tremendous productivity. It's far more productive than any other country in that region. So people have been fighting over Ukrainian soil for a long time, and you can see why, because it is so productive. So while I was writing the book in the spring of 2020, the person I will tell you about in a minute, my researcher and I found this amazing photographer who did some of the most gorgeous work I've ever seen of nature photography, and particularly of soil. His name was Anton Petrus. And so I had the idea, maybe I could find a picture of a Chernozem and put it in the book. I couldn't find one online that really captured that richness. So I wrote to Anton and I said, Anton, do you know what a Chernozem is? And I could hear him laughing over the internet. He said, of course I know what a Chernozem is. I'm Ukrainian. And of course, this is their special soil. I said, okay, well, since it's spring, would you be able to go out and get me a picture of a Chernozem before your corn or whatever crops you're planting gets too big and obscures the soil? He said, of course. So he ran out. He lived in Kiev. He ran out to the farmland around the city, and he took a ream of pictures for us. And I think this one shows might be a little hard to see in the light, but it shows that dark, rich, fertile, wonderful soil that is so productive and therefore fought over across the world. But even Ukraine It's probably the most outstanding, probably the best known characteristic of that country is this amazing soil that only spans a little bit of other countries around it. Most of it is in Ukraine. And even so, this is an example of erosion of Chernozomes in Ukraine. You can see these deep gouges out of the land. These are deep gullies. This is, for example, the kind of erosion that isn't measured when USDA measures our erosion. But you can see the massive chunks of soil that have been removed. And in fact, the European Union has gotten so upset because so many countries depend on Ukraine's agricultural production that they have actually offered assistance to train farmers in the Ukraine to treat their soils better, to preserve those soils. So far, we don't know if that's working, but we sure hope that they protect their beautiful Chernozomes. So of course, the US is not the only place where soil is eroding, and it's eroding much faster and much more aggressively in other parts of the world. This is a picture from Africa, where you can see this cutaway of land. I sort of think it looks like the earth bleeding, and I think it's a metaphor for what we're doing to our land and our soil. And so every country has erosion to different degrees, and everyone, I think, is struggling with what to do about it, some more successfully than others. So if we lose a lot of our soil, a lot more of our soil, what's going to happen? So we have soil as the largest repository of carbon on terrestrial carbon on Earth. So that's a pretty big bank of carbon that's going to be released somewhere, whether it's waterways or into the air. We've already lost 133 billion tons of carbon from soil. That's the equivalent, just to give you a sense, of 25 years of US fossil fuel emissions. If we could put that back, what would the world look like? 133 billion tons of carbon going back into the earth could make some progress toward reversing climate change. Now, that's a hard thing to do, but soil scientists are working very hard on strategies to make this happen. So if you look at this graph, the lowest bar is, just for comparison, the total fossil fuel emissions on a yearly basis across the world, so almost 10 gigatons per year. And the bars are estimates of the potential of the Earth to sequester more carbon with our help. And there are very conservative estimates. If we got just a few practices changed, we might be able to increase by maybe half a ton per year of carbon. If we use a moderate estimate that many people think is quite feasible, we move to more like 1 ton per year, gigaton per year, sorry. And if we go to the very extreme and optimistic view of what we could accomplish if we changed our practices, we get up to 3 gigatons per year, which is about almost a third of our emissions on an annual basis. So that could make a real difference. I personally think every bit makes a difference when it comes to climate change. And even if it's just this small amount, even if we just increased carbon deposition by 0.5 gigaton per year, we should go for it. And so the question is, how do we do this? And Indigenous people across the world have shown us this for centuries. The Indigenous groups that have survived, that are still living today, are the ones who successfully farmed their soil for a long time, which means they protected it. And there are many examples of that around the world. The Maori, who we heard about tonight, the Maya of Mexico and Central America, the Ifuego of the Philippines, who developed the methods of this kind of terracing to prevent soil from sliding down mountains. And then the Zuni Indians from the Southwest have figured out with extremely harsh environments how to preserve the soil, and have taught European settlers how to do it because they couldn't farm it. So what are the methods? And I'm just going to mention these. We can talk about them more later. There are 3 big methods that make a difference. One is not to till the earth. So get rid of those plows and plant by other means so that we preserve soil structure and make it less vulnerable to erosion. Cover cropping. If you fly over Wisconsin in the winter, about 8 months of the year, most of the fields are just wide open. You just see bare soil. That soil is very vulnerable to erosion. It can blow away, wash away. And we need to put cover crops in, so plants that live over the winter in the soil, partly to anchor the soil and partly to increase the carbon in the soil. And finally, there's some beautiful work based on many examples from indigenous people, including the Maya, that have led to the model called the STRIPS model. This is developed in Iowa by Lisa Schulte-Moore, and she just actually won the MacArthur Genius Award for this work. And what she's been able to do is show that by taking only 10% of the corn crop out of commission and replacing it by these strips of mixed prairie plants, she could reduce erosion by at least 90%. Some of her experiments, 95%. So this is a dramatic change, essentially over one season. So we could really halt erosion if we wanted to. We just have to decide to do it. And so I think we have a big choice at the moment. Are we going to continue destroying our soil and be out of soil in many parts of the world pretty soon, in most of the world probably in a century? Or are we going to make our soils last by changing our farming practices? That will make our crops healthier because the soil will be healthier. The farming will eventually be more profitable. Initial changes are always hard for farmers, so we have to figure out ways to get them over that financial hump. But after a while, the increased fertility of the soil reduces their costs and will make the farming more profitable. Our waterways will be cleaner because they won't be receiving all these soil deposits, and we will be keeping carbon in the soil rather than releasing it. So I guess the question I ask with the title of my book and I share with you is, will we have a world with soil? And are we going to do the fight that is necessary to change our practices, give the incentives to farmers to practice good soil stewardship and keep our soil on Earth and where it belongs? I just want to finish by mentioning a couple of very special people who helped with this book. Many, many people helped with it. But Kayla Cohn is here with us tonight. She came from London for this event. She started out as a researcher on the book right out of college and rapidly became a real partner in developing the book. She is an incredible editor, writer, and thinker, and it was a lot of her arguments that kind of pushed the book in directions that it went. Another key person was Jean Thompson Black, who's my editor at Yale Press. And if you ever want to meet an amazing science editor who is really one of the most remarkable readers and editors I've ever worked with, Jean Thompson Black, I owe enormous thanks to. Martel den Hartog is a member of my lab who helped us with a lot of the references, read the whole book, and has done an enormous job. She also, if you've gone to our website, did our beautiful website. So with that, I will stop and call on the other Kayla, Kayla Young, to moderate our discussion.
Hi, everyone. I don't know if this is, yes, it is. I'm Kayla. I'm the higher ed reporter at the Cap Times, and I'm here today just to ask Alfred and Joe a couple questions, and then we'll open it up to you all, both online and here in person. So Alfred, I want to start with you. You spoke about the history of social science in your remarks. What else can we learn from the past to conserve our soils now and in the future? Soil science.
No, I could say a few things about social science, but they wouldn't be too accurate. So,
sure.
I think what we can learn is, of course, it makes sense to care for soils. but we can particularly learn that good soil science is very fruitful. And it's not enough, I guess, and you see that a lot, it's not enough to say soils are beautiful and we need to care for them. It's also needed to do proper science on them. And for example, to make a little bridge to some of the things that Dr. Handelmans was saying is, we understand erosion, but we don't understand why it's still happening. And that, I believe, is largely a scientific question. Or maybe an economic, but economics is no science yet. So,
sure. And Joe, how would you respond to that?
Well, I think we know a lot about why erosion happens and how to stop it. But I was just having a discussion this afternoon with some wonderful scientists from John Deere Company. And one of the themes of that discussion was, we just don't know enough. We need so much more knowledge in soil science. And if we had the kind of investment in agriculture that we've had for the last 70 years in health, in human health, I think we would be able to solve a lot of problems like this. And I think we need very interdisciplinary approaches, because soil is by nature interdisciplinary. It's chemicals, it's physical forces, it's biology, it's weather. And I think if we pull together large teams, as has been done for things like developing a COVID test, I think we would solve this problem.
Sure. And so part of your expertise I've seen in your book is that you kind of are able to translate complicated soil science things to a non-specialist audience. How can we get people to care about this and to raise awareness of soil and soil erosion?
Well, I did my part. I wrote the book.
You're done.
So my hope was that it would get a few people to care about soil science. But I think we also need a multi-headed approach. This is something I tried in the White House, but it just didn't work for a variety of reasons. I think we need fiction that talks about soil in real terms. I think we need movies that introduce the reality of soil. It's said that The Day After Tomorrow, people may have seen this, it was a 2004 climate change film, had about tenfold the effect in terms of numbers of people who saw it as Al Gore's Inconvenient Truth, which was another alarm about climate change. So I think fiction and movies and all of the media have been shown to be very powerful tools in making social change. I think we could be using them. And then we need government to help us with policy.
Mm-hmm. And Alfred, so you work with college students. What do you think they find interesting about this issue, and what gets them engaged?
I think they like to see connections, and they like to see things they know themselves and how that is affected by global issues. I think the thing that we call is the environmental challenges, indeed related to climate or food security, water security, biodiversity. And they like to see how that connects to their world, I believe. And so some students at the beginning of a class or a course ask this thing for what the course will cover. And I said that's maybe not as important as what you will discover in the course. So I believe the thing of discovery, they say, hey, actually that carbon is an issue, yeah? That relates to CO2 and the heating up of the planet and the change in the weather and catastrophic events and all that. So once you've made those connections, and in soil science, in that sense, we have a very easy topic to teach. It's a very easy thing because it's so obvious to us, obviously, but also to many newcomers. It's a very obvious connection.
Mm-hmm. And so we heard about the potentially devastating effects of soil erosion. Tell us some actions we can take now to address this, and what are some ways that people can help conserve soil from their own backyards?
I think one of the most important things we can do is put pressure on lawmakers, because most of the problems we have with eroding soil could be fixed through economic solutions, just by giving people incentives to do the right thing. So that's the first thing, is to advise the president to make soil a priority and take actions that will protect it. In the book, I talk about, and a group of people wrote a policy statement recently that delineate some of the local things that we could do, like having soil cities. So tree cities were developed years ago that were named if they met certain criteria for protecting and increasing the tree population. I think we could do the same with soil. We could have soil cities or earth cities if the city participated in composting, which is something everyone can do in their backyard, but municipal composting is definitely more effective because you get the experts doing it. And then all the many things that they could do to plant perennials and keep deep, rich soil growing by having the plants there that would feed it.
Mm-hmm. Thank you. And Alfred, what do you think?
Well, I think you should not fertilize your lawn. Very simple. That is a very easy answer because much of the greening of the lakes is related to the phosphorus applications on the lawn. And don't use Roundup ever. I mean, there's a very few things. There's no reason, unless you eat from your yard. But there's no reason to use any of that in your yard. I think there's no reason not to go organic, I should say. There's no reason to phosphorus use on your lawn or use Roundup or any of that. I think erosion is maybe not an issue, but runoff is an issue. So that's the water that moves over the land and then picks up a little bit of phosphorus that people have applied and then ends up in the lakes. Well, we know what comes from that, yeah. So I would say that that's an easy solution. And indeed, plant perennials and enjoy wilderness.
Mm-hmm. Absolutely. So now we'll open it up to everyone here in the room and online. I believe you can submit questions through Zoom. So if we have any willing volunteers.
I can maybe start with some of the questions online while people in the room are thinking about it. And I'll just mention to the audience, we might go a little bit late, so leave if you need to leave, but this is a fascinating discussion, so stay if you want to stay. Larry Johnson is asking, is Putin's interest in Ukraine actually about the soil related to food security for Russia? Do you think that President Biden is aware of this possible reason for the military buildup along the border?
It's an interesting question. With Obama, I could answer that. I gave him a book that was written by a Yale professor called Black Earth, which is about the history of invasion of Ukraine by people who wanted the soil, like Hitler. And he wrote a very strong piece at the end that we're about to see even more invasions because Russia clearly needs the land. And it was, I believe, a few months after I gave Obama the book that we did see invasions, and we're now being threatened with more. So I don't know if President Biden knows of that connection, but I would guess that Putin is, in part at least, after the soil. But I have no evidence for that. It's just historians' predictions.
Could give him a call. We have an anonymous attendee who has a question. UW, through the College of Agriculture and Life Sciences, owns several thousand acres of land. To what extent does this land have cover crop coverage during the winter, if either of you knows about that?
A few years ago, the experiment stations associated with the university were all going to go to very soil protective practices, no-till and cover crops and intercropping. And I never heard the result of that because soon after that, COVID started. So Alfred, maybe you know.
No, I have not.
It's a great question.
Yeah.
Do feel free in the audience to come on up to the microphone, but we have a couple more online that I can keep going through. I want to encourage people to bring their questions forward online as well. Another anonymous attendee asks, I had thought geoengineering had a bad name in climate control circles, yet it seems that efforts to sequester more carbon in soil are a form of geoengineering. Should I think more favorably about geoengineering now that I know it includes carbon sequestration in soil?
I don't consider adding carbon through photosynthesis and plant growth to be a form of geoengineering. I think of geoengineering as injecting carbon deep in the earth, and we don't know the results of that, just like we didn't know what fracking would do when we first started fracking. I think using a process that has been going on since, for a billion years or so, should be a good process to use because it was selected by evolution, and returning the 133 billion gigatons that we've lost from the soil, I think can only be a good thing. So no, I don't consider that geoengineering if you think of it as the negative.
One more question from an online audience, and we still have some time. Karen Schloss asks, or says, Joe, this was such a fascinating talk. Would you explain more about the obstacles to getting farmers to plant cover crops and how those obstacles can be overcome?
Most of it is economic and some of it is tradition, but farmers just don't have the margins to take risks and they don't have the extra margin. For example, to take 10% of their corn out of production. That's a serious thing to ask farmers to do. When I was in the White House, I approached several groups about that, and they all came up with the same answer. If we plant 10% less corn, we get 10% less crop insurance. And that's just not manageable. But that's very short-sighted on the crop insurance side because we will see fewer disasters if soil carbon is increased. There'll be fewer droughts and there'll be less flooding. And farmers all over Wisconsin and the rest of the country have shown that. But it's getting them over that hump, getting them past that first cost, which is intrinsic. So some of us have recommended that we have, instead of crop insurance, we have soil insurance, and that it could be based on the increase in soil carbon each year, and that every year the soil carbon increases, the premium would go down. And my guess is that the insurance companies could make a lot of money that way because they'd be having to pay out a lot less. So that's just one example of the kind of perverse disincentives that we have with many of these laws that go back many decades.
This is a pretty intense walk up here, to be honest. Thanks both for speaking. I was just wondering, especially with this talk about carbon and kind of promoting good practices to sequester carbon using, less tillage, et cetera, and crop insurance. You had mentioned perennial agriculture and John Deere a few times. Is there anything that's being done in the industry to drive perennial agriculture? Like, is John Deere going to come up with a bunch of implements for planting trees or elderberries? Or I guess I'm just curious if the focus could be if there's a necessary cultural shift, because just growing up in Wisconsin, it doesn't seem like there's going to be less acres of corn. And I get that because I work with farmers, and like you said, 10% corn, less crop insurance. Well, maybe we need a different system if we're going to actually address the problem here and stop insuring bad practices for the environment. So I'm just wondering if either or both of you could speak on that.
I think it is a cultural change that's needed, and then it's also the economic part of it. So another example of how we could create incentives is to create food that is labeled soil safe. So something like the organic food idea, you pay a premium because the food had been produced under conditions that were safe for the soil, that built the soil instead of destroying the soil. We'd have to have some sort of certification process for it. That would then, we'd have to work on how to do this, but return hopefully some of the premiums that people paid in the grocery store to the farmers. And if that were a possibility, I think we would see pretty rapid change. Crop insurance and premiums and anything like that that will get farmers over that challenge of changing practices, I think we'll see. And yes, John Deere and other companies are working really hard on things like planting perennials and and one thing they're really trying to do is measure the soil carbon. It's really hard to get good estimates of soil carbon. So how can we increase something if we can't measure it? And so that's a big focus of their work, is using good metrics for following soil health.
We have two more questions online, and then probably we should wrap at that time. And I'll just mention, even though I asked Kayla to do it, you guys are sticking around to sign books after, is that right? And I think we probably still have some more refreshments outside, so I want to encourage people to stick around if you can. Tim Overdeer asks, how far are we from a carbon credit system, and do you think this would help fund and incentivize soil conservation?
I think the carbon credit story is complex, so probably don't have time to go into all the parameters here. carbon credits are already here to some degree. And I think we will be seeing that as a fairly major incentive for farmers to return carbon to the soil. But we have to monitor that system carefully so that it's not misused and distorted.
The last question we have is from Andy, who asks, where has all the lost soil ended up and can we recover it?
Great question. The lost soil is sometimes buried in another part of a field where it's not useful to the farmer. So sometimes it doesn't go very far, and sometimes it doesn't release carbon from it. But it's not useful to the farmer that had the original soil. Other times it goes into waterways and the nutrients can be released from the soil particles or travel with the soil. And that's why the Mississippi River looks the way it does. And the Gulf of Mexico has a 7,900 square mile hypoxic zone, an oxygen-free zone, which has pretty much destroyed the shellfish and fishing industry of the Gulf of Mexico. That's all the results of Midwest farming. And some of it is just nutrients flowing in, but some of it is the soil itself.
Great. Well, if you would like to wrap us up, Kayla.
Well, that's all the time we have. And both of you will be here to talk further if you have any other questions. So we have refreshments outside, but thank you so much for coming out here tonight. Great conversation.